Yeah, it looks like it's recording now. The resolution has not changed.
Yeah, if these can be recorded, that'd be great.
Okay. Yeah, as long as the resolution, as long as it doesn't mess with the resolution.
Yeah, if it doesn't get glitchy or mess with the bandwidth, then I'm cool with it. It just on my end, it was getting glitchy last time, so
Yeah, it looks good. It
looks good. So hopefully, if it behaves the way I expect it to, then this should save to the cloud on my end, and I can upload it to YouTube. So, all right, it's 11 o'clock. Cool, rock and roll. Let's see. So Canvas was down yesterday, which caused worldwide pandemonium. One of the reasons I didn't
up enough to make it really panic, but it wasn't closed long enough to change hardly anything, which I'm still a little mad about. Because none of my due dates have changed. And I'm like, oh
no, sorry. Yeah, I was sort of hoping for global economic collapse, but
Yeah.
didn't happen. So we all have to go back to work. So good news. I owe y'all a lecture for yesterday, which I haven't posted, in part because of the Canvas meltdown. But I also was looking at the schedule, and we are making really good time through this material. So one of the things that I want to do, because I feel like it's unfortunate that there's just so much material in this class that I often don't have the time to do, is I want to do a lot of problems, exercise problems that you guys can watch me do and think about, and just basically model solutions. And so based on the schedule that I've written, we weren't supposed to be getting to 9.7 until next week. So that means that after today's lecture, we will be 2 lectures ahead of schedule. And I owe you a lecture. So what I am going to do is, for after today's lecture, the remaining lectures of the week will just be practice. Instead of trying to get ahead of schedule, I'd rather just work problems from 9.1 through 9.6. So I will post a lecture that I owe you for yesterday, which will be just practice problems. And Thursday and Friday will just be practice problems. So there'll be 3 full lectures of doing nothing but practice from 9.1 through 9.6. So we'll be able to cover a lot of problems and see a lot of different variations on a theme, which I'm really excited about, because I think that that's where most of our weaknesses are. It's just so much coming at us that we don't have enough time to look at everything. So it'll just be a ton of practice problems. That being said, that means that the quiz on next Monday will cover, let's see, we did basically 9.1, 9.2. It's all kind of a continuum. So it'll cover 9.3 through 9.6, but other than sequences alone, without a series involved, it's basically all the same material. So that might be a slightly juicier quiz just because it can cover so much more material, but you'll have seen a lot of practice problems by then. So, and hopefully you've followed along and studied the ones that you think are tricky or whatever. So I'm using, hopefully yesterday's quiz wasn't too harrowing. The methodology that me and Nick have settled upon is, or like the motivation or goal is to get you guys to do this stuff by modeling problems that are pretty closely that mirror the structure of the quiz, so that you have a good example walking into the quiz, and you just have to sort of modify the thinking according to the numbers or whatever the slight structural differences on the quiz. What I want to see is that you can do it on your own, provided you're given a good model, and that's what we're trying to do with those quizzes, so that the problems might be a little bit juicier, but Nick is going over one that is almost identical to the juiciest one on the quiz. So I feel like that's totally fair. I would have loved to have had that arrangement when I was in Calc 2, but my professor wasn't quite as nice as I am. So, all right. So we're going to get into the lecture material now after that update. Today, we are talking about, we're on 9.6 today. And like I said, I owe you lecture, and that's just going to be practice from 9.6 onward. So you'll just have a ton of practice stuff. So today we're looking at alternating series. And we're just going to jump right into it on this one here. So, we've already been looking at alternating series before. We just haven't come out and called them that. So we'll state the theorem, and the definition will be of what an alternating series is will be evident from the theorem. So suppose we have a series that looks something like this. So it's an infinite series, and the terms in the series are alternating signs. So plus, minus, or minus, plus, minus, plus. It doesn't matter what the ordering of the alternation is, it's just alternating. So every other term is a different sign in an alternating series. So supposing we have such a critter, then I can say this is convergent if the following conditions are met, okay? So what must be true? First, the sequence AN, stripped of its alternating component, must be strictly positive. We don't want AN to be alternating signs along with the alternating component here, because that could cause issues. So we restrict it to only being positive. So we have a positive sequence AN. We also want it to be eventually monotonic, non-increasing. So in other words, eventually the terms are getting progressively smaller for all n greater than some bound. I'm sorry. Right, so it doesn't have to be true for all points in the sequence, just eventually it's true that we have a non-increasing sequence. So, verbally, that's what we would say. It's non-increasing. All right, lots of conditions to check. And finally, this is an alternating series, yes, but it is a series, period. So if we want it to converge, we know that the corresponding sequence must go to 0, right? So that's a theorem that we already know. No series converges if its corresponding sequence does not go to 0, period. So that must also be true here. Right, so we say this converges. All right. And what is this? This theorem is called the alternating series test. So when we're invoking it in our solutions, that will be the name that we call it by, the alternating series test. If we feel so inclined, as we'll see in applications, we don't really come out and say that quite often. We're just kind of running through the litany here. All right, so a rather paradigmatic example of how this type of convergence that we're looking at here is sounded counterintuitive. Is here we're looking at an example which is the alternating harmonic series. So it's alternating and it's harmonic, and we know from our P-series experience that if we took away the alternating component, the standard harmonic series is divergent. But as you'll see, if we check all the conditions for this guy, the alternating harmonic series will actually be convergent. So we check the conditions. 1 over n is indeed always positive. Check. Is it non-increasing? That would mean that 1 over n plus 1 should be less than or equal to 1 over n eventually. And if I do a little bit of algebra, that would imply, if this is true, then it's equivalent to saying n is less than or equal to n plus 1, which is true. So it is non-increasing. And indeed, 1 over n goes to 0 as n goes to infinity. So all the conditions are met. Therefore, we'd say by the alternating series test, the alternating harmonic converges. So that's a rather interesting consequence. One of the many places where analysis does something that doesn't kind of goes against the grain of our intuition. So a regular old garden variety harmonic series is divergent, but the alternating sibling to it is convergent. Okay. Questions about this so far? Nope. So far, so good. All right, so we're going to keep that theorem in the back of our heads. We know we have to check the conditions. You do not get away with not checking the conditions. I'm saying that as a word to the wise. Okay. This is, just like when you were doing the mean value theorem in Calc 1, you've got to check the conditions before you can apply the theorem. If you just go out willy-nilly, half-cocked, and start using the theorem without checking the conditions, you can get bad results. So always check the conditions. All right, so let's look at some more examples. Well, one consequence here is if we generalize this and we look at the alternating P series, right? So now not just the case when P equals 1, but for any P, we find that no matter what the value of P is, we have a convergent alternating series. So that's pretty awesome. So as long as P is greater than 0, then this guy is convergent. All right. But what we're going to look at now is there are basically two flavors of convergence. So we're saying these things are convergent, but they're convergent in a particular way that we have to distinguish between other types of convergence. And so again, this holds by alternating series test. I'm just going to say AST. Okay. So definition. A series AN that is convergent but not absolutely convergent, we say converges conditionally. Or we'd say it is conditionally convergent. So this is just terminology. It's conditionally convergent or it converges conditionally. So this is a different flavor of convergence. And this is another case where the logical flow is only unidirectional. So if we were to kind of make a nice little, we were to boil this down to what it's saying if I have a series that's absolutely convergent, then that obviously implies normal convergence. However, if I have a series that's just normally convergent, that does not imply absolute convergence, which we've seen. This was also a consequence of, when we're talking about absolute convergence, we said this is how it works. Absolute convergence is a stronger condition. So now we have a name for this situation, right? So this logical consequence follows from the definition of absolute convergence. But now we know when we have a situation like this, we'd say that this sequence is conditionally convergent. So AKA, our sequence is conditionally convergent. But it is an important logical consequence. And so this idea here is going to prompt how we navigate problems going forward. We want to, when we're looking at a series, we want to check that it's first whether or not it's absolutely convergent. Before we check any other type of convergence, we should check absolute convergence, because if it is absolutely convergent, then we get everything else for free, right? If it fails to be absolutely convergent, then we need to look at whether or not it's conditionally convergent, right, using the alternating series test. So this sort of prompts our approach to solving convergence problems. First, check absolute. If not absolute, check conditional. So yet again, we could just look at the alternating harmonic series. We did find out that this is convergent by the alternating series test. But if we look at the absolute value of this series, then we're looking at the regular old harmonic series, which we know is divergent by P series test. I'll just say PEST. How about that? So what does that imply? That implies that the alternating harmonic series is conditionally convergent, right? So it's a subtlety, but it is an important one, and one that you have to write down clearly. We're saying it has some sense of convergence, but it's not convergent in an absolute sense, right? So this is a stronger claim. But it's interesting that you could have these two different flavors of convergence. So if we go back yet again and look at the general P-series test, the general alternating P-series, or generalize this result, what does this tell us based on our analysis, we can say if P is strictly greater than 1, then we get absolute convergence. But if P is less than or equal to 1, then we only get conditional convergence. So this is a quick and easy thing. You know, I could throw this on a quiz or an exam, and it's a bing, bang, boom kind of situation. If you can make this statement, then you're done, right? And it's an important connection to make, that alternating series behave differently than normal series, and they have a different notion of convergence that is native to that type of series. Okay. So let's get down in the weeds here, right? Let's start doing some problems. But before we do that, actually, there is one important note. What I'm about to show you won't really come up computationally. You know, like you won't be using this idea to solve anything, but it's a good one to show just to make you a little bit more sensitive to what's going on here. Okay. So, and it's a neat little proof. Comes with a theorem. I'll just call it the rearrangement theorem. So what does it say? It says, if I have a series that is absolutely convergent, and I take that series and I define a new series, Bn, or I'd say a new sequence, rather. I define a new sequence, which is a rearrangement of the terms in An. So, you know, B1, B2, B3, these can be different. These can be the elements of An, but out of order in some different sequence of some different arrangement, right? So, I mean, just as an example, just to make it clear, suppose B1 equals A3 and B2 equals A1 and Bn equals AK for some, you know, whatever. It just, we're just scrambling the order of the sequence. What this theorem says that if we have an absolutely convergent series, then rearranging the terms in that infinite sum, which remember, this is an infinite sum. So it's not trivial to say this. You know, it'd be one thing if it were finite, then we could actually check all the possibilities, right? There's only a finite number of ways to reorder a finite number of items. But for an infinite list of items, there's infinitely many different ways of reordering them. So this is not a trivial statement. But if this is absolutely convergent, then any rearrangement is also absolutely convergent. So I can take the terms and rearrange them any old way I want, and I'll still end up with a convergent series, assuming I started off with something that was absolutely convergent. So fine, okay, that's cool. But here's the consequence. If I start with something that's not absolutely convergent, then I can rearrange it in some way potentially that I'll get something that I'll produce some sort of contradiction. It'll violate the laws of logic. So this is a cool little example. We know that the alternating harmonic series is conditionally convergent, right? So that means it goes to some finite limit, but only conditionally. So suppose we call it that limit L, then if I look at 2L, that should be equal to 2 times this alternating series. And so what does that look like? If I look at this term by term, that's 2 times, the series is starting at 1 and going to infinity. So we'll have a 1 minus 1/2 plus 1/3 minus 1/4 plus 1/5 minus 1/6, and so on, alternating. So if I distribute that 2, I'll get 2 minus 1 plus 2/3 minus 2/4 plus 2/5 minus 2/6, so on. And if you look down this pattern, you're going to see something happen here where I could rearrange this so that I have 2 minus 1. And then if I take the 2/3 here and that negative 2/6 here, I can move that up. 2/6 is 1/3. So I can do something like that. And then I've got a minus 2 over, where am I at? Minus 2 over 4. So actually that should have come first. Hold on, make this point. So we got 2 minus 1 minus 2 over 4, which is 1/2. Then I move up that negative 2/6 here, and then we'll have a minus 1/4, and so on. So it doesn't take long if you stare at it to realize that I can rearrange the terms so that what I get in the end is 2 minus 1 is 1 minus 1/2. 2/3 minus 1/3 is 1/3. And then I get a minus 1/4. And then if I kept this pattern going, I would get a 1/5, and so on. And then you notice and you say, hey, look, that's the alternating harmonic series. So this thing should go to L as I compute that infinite sum. All right, so I took the terms, I rearranged them, and I got the alternating harmonic series. So what's the conclusion? The conclusion is that twice the harmonic series is equal to 1 time the harmonic series. In other words, 2 equals 1, end of proof, right? We've made a profound contribution to mathematics. We've changed the world. We've proven that 2 equals 1. But of course, we know that that's not true, right? So we got a contradiction. The mathematicians love coming up with ways to represent contradictions. One of the ways that I like is 2 arrows pointing at each other, so they're butting heads. So why did this happen? We ended up with a contradiction because we started with something that wasn't an absolutely convergent series, and we rearranged its terms, and we got something that didn't, that made sense. It's totally right, but because we started with something that was not absolutely convergent, we're able to arrive at a contradiction by rearranging the terms. So conditionally convergent sequences or series, their convergence and the nature of their convergence depends intimately on the ordering of the terms, which is kind of bonkers. Because with sums, we assume that everything's commutative and transitive. We can move things around and rearrange things, and sums should always equal the same thing. But when we're dealing with an infinite sum that's alternating, then when we add a certain thing or when we subtract a certain thing matters within the sequence or within the series. Sorry. So that's a cool little result. I like it. Not going to test on this or anything like that. That's just something I wanted to show you. It's a neat proof that this statement actually has import. It's important to make this distinction because you can end up with weird stuff. All right. So now we can look at some problems. So for all intents and purposes, you have seen the full arsenal of tools and techniques for determining the convergence and or divergence of series. With the alternating series test, you've got a full quiver of arrows now, right? So now you should be able to look at a series and using one or some combination of the techniques that I've shown you, assess its convergence or divergence, and maybe even potentially find out what it converges to. Okay. So let's look at some examples. All right, so we're looking at this infinite series here. It's alternating, right? So we know that we have to look at this carefully since it's alternating. Right, so what should we do first? When we're looking at something like this, always the prompt is it convergent or divergent? And state why, right? So when I begin looking at this thing, my first stop should be, is it absolutely convergent? Because if it is, then that covers all possibilities. And so it's a much stronger sense of convergence. So I always want to check that first, right? So I'm just modeling the thinking here. So your first thought should be, is it absolutely convergent? Well, let's take a look. So I'm looking at the absolute value of the sequence here, and that's just going to get rid of that alternating term. All right. And you look at this thing, and you have to start kind of using your gut to give you a sense of which direction you want to take with this. So if I'm looking at this series, what is our vibe? Do we think that this is convergent, or do we think it's divergent when you see that?
It's like,
go ahead.
It looks like 1/n squared, which is like P series, so maybe convergent.
It kind of looks like 1/n squared. Well, you got to be careful with that because, natural log of n, that has a different nature to it than a linear. If I think, I think about this graphically, n is a linear function, right? And I'm just going to use it. I'm going to plot it as something continuous. Actually, it's a bunch of points, but it's easier to see it that way. So that's what n looks like. But what does natural log look like? Natural log looks like this. Yeah. So they shouldn't intersect. At least I'm not remembering. I don't think they do. But it doesn't matter. Eventually, even if they did intersect, eventually, because n is growing linearly, in a straight line, and the natural log is bending, right? It's bending away from it. The natural log is not growing as fast as n, right? Natural log is one of the slower growing functions out there. So if it grew as fast as n, I would agree with you, but it grows slower than n. So it doesn't look like it looks like something less than 1/n or greater than 1/n squared. It doesn't behave quite the same way. So you want to start getting a feel for this. When you have natural logs, they're slow growing. Factorials are fast growing, right? And n to the n is the fastest growing thing we know, right? So you got to kind of think of the spectrum here. How fast are these things growing? Natural log grows kind of slow. So since it grows slower than n, and we know that 1 over n is divergent, I would expect 1 over ln of n to be divergent. But what about ln squared? I mean, maybe when I square it, it will grow faster, fast enough that it converges, right? We know that 1 over n is sort of a threshold. So if we can get it, if we can show that 1 over ln squared grows faster than 1 over n, then we would have convergence, but maybe not. So how do we think about it? What do we compare it to? Well, ln of n, I mean, we learned this, right? I showed you this fact. Ln of n is smaller than nc for any c greater than 0. So it grows slower than any power of n, which is kind of profound. So you always want to have that in your back pocket when you're thinking about the natural log. So in particular, I could say the natural log grows slower than the square root of n. And if that's the case, then since everything is positive here, this inequality holds. Which in turn implies that 1 over n is strictly less than 1 over ln of n squared. It's never good to be bigger than 1 over n. So if you're bigger than 1 over n, then since we know this is the harmonic series and it's divergent, that implies that 1 over ln of n squared is also divergent. And remember why that is? That's by direct comparison test, DCT. The 4, again, don't get caught up on the 4. That in the scheme of convergence, that 4 has very little role to play. So if this is divergent, then certainly 4 times it is also divergent. Right? So we've established that this critter is not absolutely convergent, right? So in other words, it's not absolutely convergent. But once we've established that, then we have to go back and say, well, it could still be convergent, right? We've got to check that it's to see whether or not it's conditionally convergent. So failing the absolute convergence test basically doesn't eliminate convergence, doesn't take it off the table entirely. So we've got that, and I'm recording, so I can erase to my heart's desire. This is great. I don't have to worry about you guys at all. So now we need to check conditional convergence. So our first question was no. So second question is it conditionally convergent? Which in other words means use the alternating series test, right? So what does that say? That says if I let, I mean, technically I should call this something else, it's just to keep my notation right. So I'll say Bn is 4 over ln of n squared, right? Because I'm using an to denote the whole alternating sequence. So we'll say that. So we got to check all the conditions. Bn greater than 0, yes, right? Natural log, since our series is starting at 2, natural log will always be positive, and it's squared anyways, so everything's positive here. All right. second condition, the harder of the three conditions to check is it monotonic non-increasing, right? Is it a non-increasing function? So is 4 over the ln of n plus 1 squared less than or equal to 4 over ln of n squared? And if you're a good mathematician, when you write things like this, if you don't know it's true, then you should indicate it, right? So I'm putting a question mark over that inequality. I don't know if this is true. Right? I can't just write it down if it's not true. I've got to at least show that there's some equivocation about it. All right, but if it were true, then that would imply that the natural log of n squared is less than or equal to the natural log of n plus 1 squared. And you've got to be careful with this because the natural log of n can be less than 1. And so when you have something that's less than 1 and you square it, you get something even smaller, right? You don't get something bigger, you get something smaller. So this statement isn't always true. You've got to be careful about that. Like, just suppose, for instance, that you had 1/2 and 1/3, and you square them. Well, if that were true, then you'd get 1/4 and 1/9. And that's not true, right? 1/4 isn't less than 1/9. So when you have something that can be less than 1, you've got to be really careful when you're squaring it. So what does that indicate? That this isn't always true, but for n greater than or equal to e, this is true. So as long as my n is greater than or equal to e, then this is true. And remember, in the statement, it needed to only be true eventually, right? So e is my big N in that statement. And yes, you are expected to make that clear. This is a part of the conditions. So it's not always true, but it's eventually true. So we're good to go. And finally, it's obvious that this thing goes to 0. So all the conditions are met, which implies that our series here is conditionally convergent. Okay, so one thing you're going to have to be careful about, because it's easy to fall into this trap. This shouldn't happen if you always follow the order, the sequence of solution that I just followed. But it could be tempting to do an alternating series test and then conclude, and it comes out true, and then conclude that your series is conditionally convergent. And that's not true, okay? That's only true because we know that it failed the absolute convergence. So conditional convergence is the complement to absolute convergence. But saying an alternating series is convergent does not imply that it's conditionally convergent, right? That's only one leg of the logic. You have to first check absolute convergence, right? Because this can be true and this can be true, and then you want to say a stronger statement, which is this is absolutely convergent, right? So as long as you go in this order, you shouldn't make that error. But it's an important point to make that just because this passes this alternating series test does not mean it's conditionally convergent. And nowhere in the language that I show you say that those two things are equivalent. This is only true because it fails the absolute convergence. All right. see what I'm doing on time. 6 minutes. All right, so 6 minutes, we'll do a quick one. So let's say we're looking at this series. All right, so I'm in y'all's hands now. I'm your puppet. What do you think? What do you see? Where should we go? Be bold.
Should check for absolute convergence first.
Okay.
Let's say the absolute value.
Does anyone else have any instincts? I mean, yes, I agree. You should always check that. But potentially something might just jump up and bite you here. Something should be screaming at you. You're looking at this and something ain't right.
It does kind of just look like for the non-alternating term n over n,
Uh-huh. Which
which
what?
I mean, that implies that that itself diverges. Well, if that part converges to greater than 0, then the series must diverge.
So if that part diverges to what'd you say?
So if it diverges greater than 0, right?
If it diverges greater than 0,
Or if it,
I think there's a better way to say it. Can someone help Daniel out here?
Do you
He's
mean
been
like,
doing a lot of talking.
like
Doesn't
if you take the 3 plus n over 5 plus n as
Uh-huh.
sequence, and then
Uh-huh.
evaluate the limit,
Yeah.
and it looks like just n over n, which
Uh-huh.
is the nth term test, which converges to 1. And
Ah,
that converges to 1, and the series cannot converge.
there we go. So that's what you're trying to say. It doesn't diverge to something greater than 1. It converges to something greater than 1, right? So before you do anything, really I should have put the first thing you always want to check before you whip out any bigger machinery is that the corresponding sequence goes to 0, right? That's a hard theorem, and that should be your first check. And oftentimes we don't even write it down because if you look at it, you can see it for the most part right away. Sometimes you can't, but in this case you can. So if we call, there's kind of two things that are going on here actually. So this is an alternating series, and this would fall out in the if we checked absolute convergence, we'd come to the same conclusion that Daniel did, and maybe you can see it right away and save yourself some writing. But we'll just follow the litany. So is it absolutely convergent? Well, then we're looking at the sum of 3 plus n over 5 plus n, since this thing is this component is always positive. And now we're just looking at this series. We're forgetting everything else, and we're saying, hey, but then if I call that an, then an does not go to 0. This is the quickest way that you can, this is a really nice problem because it's a snap of the fingers. Hey, look, the sequence doesn't go to 0. Therefore, by that theorem, I don't even know if I give it a name. By very important theorem that has no name. Maybe we should come up with a name. our series must be divergent. Do we want to come up with a name for this?
Just call it VIT, very important theorem.
Well,
Very important.
I think it should be
Fit.
the Daniel theorem.
What is it called?
I think it should be called the Daniel theorem.
The Daniel theorem. Okay, I think your ego is big enough, homie. We're gonna we're gonna leave that one alone. But yeah, we'll call it the VIT. I like that. So if you use that on a test or a quiz, I'll accept it. So by VIT, our series is divergent. And if it's divergent, it's definitely, it's done. It can't be conditionally convergent if it's divergent, period. And we'd see that too. If we applied the alternating series test, this would fail there too. So, all right. I'll see you guys, not tomorrow, but the next day. I will be posting a video to make up for the lecture on Monday. It'll be more practice problems. And the rest of the week will just be running problems. So I'm excited. Y'all have a good day.
Thank you. Like my idea. That.
Understood.
Thank you. There's some good thing on it, so.
Nick, you can go ahead and stop the recording.
Okay. But if I hit the stop button, is it will automatically save your cloud for you?
Yes. Yeah, just hit stop.